first thing for this semester we need to cover is a quick review of summation notation. You may have seen this in Algebra 2, pre-calculus, or college algebra. And is a way to use shorthand to show the sum of a sequence. For example, if I have the numbers 1 plus 2 plus 3 plus 4 plus 5, I can write shorthand that I want to sum from n equals 1 to 5 the first 5 numbers. So these two are equivalent. So this says replace n with 1, then replace n with 2, with 3, with 4, with 5. We start with this integer, we stop with this one, and we put plus signs in between the two. This E-looking symbol is actually the Greek letter sigma, and sigma starts letter S, so does the word sum. And what we're going to use is we're going to use this similarly the way we use limits during first semester. We're going to use this as one of the motivators for the calculus that we're going to use for second semester. Two handouts that I'm giving you. One just basically has the rules that I'm going to be writing down on the board, and the second one shows you how to use the graphing calculator to come up with, if you're given this, how to enter it into the graphing calculator in order to find a particular answer. So let me just do a couple examples for you. But before I can do the examples, I need to talk about these properties. So we have basic property that if I take the sum from, let's say, I equals 1 to n of a constant. For example, if the constant was like the number 2 and that n was 5, it would say add 2 5 times. Well, basically what it's telling me is if I'm adding the same thing over and over again a certain number of times, I'm just going to basically be multiplying my constant times that number of times. Another property of summation notation if I have two functions that have something to do with the I can actually break these up like we broke up our derivatives and our limits, as it can be the sigma of a sum is actually going to be the sum of the sigmas. Similarly, I can do the same thing for differences. And where this is going to come into play is this is going to help us break apart polynomial functions. And we get to thank the mathematicians from way back when. They actually gave us some formulas that we can use for finding the sums of the first n integers, the first n squares, and the first n cubes that we're going to use to evaluate sums of some polynomial functions. So the formulas that we're going to end up using are the first one, the sum of the first n integers, I equals 1 to n of I, so that's saying put 1, and then go to 2, go to 3, go to 4, go to all the way to n. So this is going to be 1 plus 2 plus 3 plus n. That's going to give me n times n plus 1 all over 2. This form right here is called open form, which means basically expand the sigma notation to show exactly what it means. And this right here is called closed form. So if n was 5, I would put a 5 here, and do the math. So 5 times 6 is 30. 30 divided by 2 is 15, so the sum of 1 plus 2 plus 3 plus 4 plus 5 is 15. The second one that we'll be using is the sum of the first in squares. In open form, that would be 1 squared plus 2 squared plus 3 squared, all the way up to n squared. And its formula is n times n plus 1 times 2n plus 1 all over 6. And the last one we're going to do is the first in cubes. So I get I equals 1 to n of I cubed. That's the same thing as 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed. And it's going to look very similar to the sum of the first integers, where it's n times n plus 1 all over 2, but this whole quantity is squared. So we're going to use these properties and these closed forms to evaluate some summations. So, for example, if I wanted to know the sum of the first 5 I squared plus 3I plus 4. So if I wanted to know what the sum of putting a 1 in here, a 2, and a 3, and a 4, and a 5, what I can do is I'm going to use my properties. First thing I'm going to do is I'm going to break it up into 3 separate summations. Just like with derivatives, I can bring that constant in front of the summation sign. And that one right there is just the summation of I equals 1 to 5 of 4. And now I'm going to use the formulas. I'm going to use this formula for the squared one. I'm going to use this formula for the integers. And I'm going to use the 4 times 5 for the last one. So for I squared, I get n times n plus 1 times 2n plus 1 all over 6 plus 3 times n times n plus 1 all over 2 plus the 4 times 5. Those 6's will cancel. That 2 will cancel with one of those in there, leaving me with a 3. So I end up with 5 times 11, which is 55, plus 9 times 5, which is 45, plus 20. 45 plus 55 is 100, plus 20 is 120. So if you were to add the first 5 integer iterations of this polynomial together, your answer would be 120. Some of the homework problems, they're going to give you a sequence that's in open form, and they're going to want to have you write it in sigma notation. And the other part of your homework problems are to take things that are in sigma notation and turn them into find their final answer. Now, if it's a polynomial function, you're going to be able to use these rules directly. However, there is 1 or 2 problems that are trigonometric in nature. So I will do an example of one of those. just so you can see how we're going to do the work. So I want to know the sum of the first 8 cosine of I pi fourths. So the first thing that I would do is I would write it out in open form. So this is what they're telling me is they want to know what the cosine of 1 pi fourth plus the cosine of 2 pi fourths plus the cosine of 3 pi fourths plus the cosine of 4 pi fourths, and we'll do 5 pi fourths plus the cosine of 6 pi fourths. 6 fourths is 3 halves, plus the cosine of 7 pi fourths, plus the cosine of 8 pi fourths. So first step you're going to do is you're going to write it out in open form. Then you're going to evaluate each one of those in open form. And the cosine of pi fourths is the square root of 2 over 2. The cosine of pi halves is 0. Cosine of 3 pi fourths is negative square root of 2 over 2. Cosine of pi is 1. Cosine of 5 pi fourths is negative square root of 2 over 2. Cosine of 3 pi halves is 0. Cosine of 7 pi fourths is the square root of 2 over 2. And the cosine of 2 pi is 1. The square root of 2 over 2 and the negative square root of 2 over 2's cancel here and here. And I'm left with 1 plus 1, which is 2. So between the two examples that I did, you should have enough information to do the first homework assignment of the semester.